Hello and welcome to another episode of AI for Humans. And if this is the first time you're joining, you have skipped 10 episodes previously. So welcome to episode 11. I advise you go and watch from episode 1. But of course, everything we will do here is quite easy to understand with a lot of explanations, obviously. So welcome. Last week we discussed deep learning. Now let's look at computer vision. You see, from episode 1 to episode 10, we've been discussing how artificial intelligence systems work, how the machines receive inputs and how they receive outputs. We understood the inner workings of prediction, how you can train a machine on data and it can use that data that's of what it has seen to be able to predict what it has not seen. 1 plus 1 is 2, 2 plus 2 is 4, 4 plus 4 is 4, is 8, and then we can easily say 8 plus 8 is 16 because he understands the addition rule, not memorizing the patterns. It's easy when you start like that, but when we begin to get into really intelligent systems, we begin to ask questions. For example, have you ever wondered, how does AI or how does your phone or how does your computer know what a picture is? How does Google, this AI engine, identify your pictures? Well, let me start with this. Look at my hands, the 5 hands, or rather, I'll just draw it. How do you know that this is a hand? How can you easily identify? You see, ideally, your first answer could be, I just know because look at it, it's a hand, correct? But the only reason why you see this, and now it's looking like a leg. So the only reason why you see this and you say, this is someone's hand, is because you could probably see what we call, you saw the fingers, you saw the nails, you see the knuckles, and you saw a palm. Yes, you see, ideally, your mind does not look at a hand and ask questions like, can I see fingers? Can I see nails? Can I see knuckles? Can I see palms? No, your hand doesn't do that. Your mind doesn't do that. Your mind sees hands and it identifies it, almost immediately. That's because your brain has been trained over and over again of what the vision of a hand is. I remember we said neural networks are simply mimicking the brain. Our minds are trained over and over again. So it's simple. Like, for example, in school, how did you learn stuff? Repetition. Repetition hence became mastery. And the same thing applies to artificial intelligence systems. So what happens when I show the same hand to a computer? What does a computer see? And in a previous episode, we had hinted on it a bit that computers cannot see images. Whenever we pass an image to a computer, the computer is not seeing an image, right? Say maybe once again, we have the hand. Computer does not see a hand. What a computer sees numbers, and these numbers actually appear in a grid. So a computer actually is seeing something like this. Don't worry, you're going to get it. A computer is seeing something like this. A computer is not seeing numbers. So a computer is probably seeing 0, 8, 72, 83, 126. I'm guessing, right? I'm not saying this is the exact interpretation, but every time you take a picture, you pass it through your phone, a computer is seeing numbers. Now, each number represents something. Because we use numbers all ranging from the way to 0 to 256. I won't go into why we stop at 256, right? But just agree that this is our range. There's a reason for this. It's back into compiler mechanics, but we don't need to go into that. But each number ranges from 0 to 256. In this grid, every section is what we call, and this is probably something you're familiar with, a pixel. Now, just hold that thought. A pixel. A pixel can have a range from what we would say from dark. Let me give this a bit more. Okay. A pixel can have a range from dark to bright. All right. So we say dark starts from 0, bright is 256. So if a pixel, in this case, one of these points in the grid is, say, has the score of 30 You can say it's not so much of a bright image, but if it has a score of 216, this is bright. There's a range. So the numbers actually help us to identify how bright or how dark each color is. This grid holds pixels, one tiny pixel. That's it. This is a pixel, 72 is a pixel, 8 is a pixel, 0 is a pixel, 83 is a pixel, everything pixels, nothing more. Computer vision, which is what we are discussing in this episode, is the art of us teaching AI to be able to go from those numbers to meaning, right? From pixels to understanding. And the way that we do this is very interesting. The only thing I want you to take right now is two things. One, computers cannot see images the way we see images. They can't interpret it the way we interpret it. They see images as numbers. Now, how we got to that point, I'll explain. They see images as numbers, and for every number, it is represented in a grid, right? It's represented in a grid. Now, for every pixel in that grid, when I mean grid, I mean this is a 1, 2, 3, 4, 1, 2, 3, 3 by 4 grid, right? This is a 3 by 4 grid, okay? And a 3 by 4 grid has 12 pixels. I mean, ideally 3 times 4, right? 1, 2, 3, 4, 1, 2, 3, right? 12 pixels. So 12 pixels. Each pixel in the grid is given a number. Each pixel in the grid is given a number. And that number tells us how dark or how bright a color is. If the number is 0, it means that that aspect of the picture is bright, is dark. And if a number is as high as what, let's say 72, we probably say this part is 72 and that aspect is bright, right? 83 bright, 36 not so bright, right? Up all the way to 256. That was the range that we drew here. So just take that. Images are converted to numbers. Numbers are converted to numbers in a grid. Pixel in the grid tells us how bright or how dark it is. Computer vision converts the picture to number. Identify what the picture is and take it down to number. Now, let's make this very concrete. Take a look at something you interact with every day. Whenever you're chatting on WhatsApp, there's a very high likelihood I could make a bet with you that in a day you'd use a smiley at least 10 times. At least, or what we call an emoji. So what are emojis like? You know, you have emojis. These are your emojis, and then you're going to have what we call a smiley face in the emoji, right? Someone like that. Once again, terrible artist. I'm probably not trying this correctly, but the idea is that, right? You have all your smileys. These are your emojis. You have so many emojis on your phone. When you pass your emoji into your computer, when you send that emoji, what you're actually sending to the computer is a grid. And that grid is what we have your emoji is stored in an 8 by 8 grid. 8. Okay, this is the 4 by 4 grid. Okay, but it's actually stored in an 8 by 8 grid, right? 8 by 8 grid, which means that emoji has 64 pixels. 8 by 8. The emoji has 64 pixels. Now, for each color image, think of, okay, so remember, great. Whenever you're looking at your phones and someone tells you that my phone has 12 megapixels, my phone has 15 megapixels, what it is simply telling you is that for every picture you take on that phone, 12 million megapixels are 12 million pixels or 12 million numbers are used to identify each picture. So once again, I'll just digress a bit where we say if a phone that has 5 megapixels should take a picture and a phone that has 12 megapixels camera should take a picture. Here, this is simply saying that you are devoting what 5 million numbers to represent each picture. Whereas here you are devoting 12 million numbers to represent each picture. And eventually that is why you have 12 megapixels has better quality than 5 megapixels. We are only giving it more numbers, and don't worry, it's going to make sense. Now, remember we said earlier that from 0 to 256, we can identify how bright or how dark a picture is. But how about color images? How do we identify that? You see, for color images, instead of these pixels having one number, each pixel is going to have 3 numbers, right? So imagine that for this pixel, we're going to save it in a matrix, in a very simple, scalar or vector quantity, whatever. So, but don't worry about that. So, we'll represent each pixel with RGB. And RGB here means red, green, blue. So, for each image that is sent, every corner of that image has a color, maybe black, maybe blue, maybe orange, right? Every corner of the image has a color. And hence, what we do is we're going to pass the color that we are receiving in that pixel. Remember, the emoji is one full image. This is the emoji, one full image. But what we'll be doing now is the emoji here, this emoji is one full image. This emoji is transferred and stored as pixels. So for every corner of the emoji, we save it. For every corner of the emoji, we save it. For every corner of the emoji, we save it. And when we do that, we are passing that result as numbers. But because this image is not black and white, it's actually a colored image, we will not pass just one letter. Remember that we did that earlier here where we said we're passing 0, 8 to 72, 36. Here we imagine it is black and white. But when we come here and it is a color image like your emojis that have red, orange, then we're going to be passing into each pixel a range of numbers. So red, green, blue. And what we are saying is at a very high point, and you're going to see where those numbers actually make sense, we're going to represent every color with maybe 26, 87, 39. If you combine these together, it will give you a color. It might give you magenta, it might give you violet, it might give you that. That's not a problem. Now, I went online and I actually checked what orange is. And orange is 255 for red, 87 for green, and 34 for blue. This is orange. And it makes sense because remember we said that from 0 to 256, it tells us how bright an image is. So 255 here is telling us that red is very bright. Green, not so bright. Blue, bright. Now imagine green diluting red, blue diluting red, and then we get orange. Little bit of chemistry, but you get the idea of what we're talking about here. But don't forget where we're starting from. We're saying that artificial intelligence system can decode images. But how they decode images is that they turn these images into what we call grids. And these grids have pixels. Each pixel is represented by what the image is, what's the color of the image. So whenever you take a picture now on your phone, and I mean, ideally, when you come to your phone now, the next picture you take on your phone of you striking a badass pose. Sorry about that. A proper pose. Right? You're striking that pose that is killing the internet. Just know that your picture is going into your phone like this. Your phone is just receiving images. It's just receiving numbers. And for each number, for each pixel, if it is a color pixel, right, it would have a range of red, green, blue values. Okay, now that I believe I have appropriately confused you, which I have not, I promise, right? You understand where we are now. You know that for every image that is passed into the system is receiving as numbers because computers cannot see text. They cannot see numbers. They cannot see images. The only thing they know is ones and zeros. How 255 is converted to 1 and 0 is binary. Ignore that. Just know that we receive 255, we receive 26, we receive 87, we receive 39, and then the computer goes one step further. Remember that in episode 10, we said that neural networks understand images and text layer by layer. And here's a refresher. We said that for each image that is received or text that is received, there is an input layer. The input layer is the one that receives the raw image, but not raw because it must have been converted to numbers. The input layer passes it to the hidden layer passes to the output layer checks the model and outputs a result. Easy peasy. That's what we said. Now, the question is, how exactly does this work? Now that we know that every image is converted into numbers that is put into a grid, and each grid has pixels that represent the brightness or the color of the image, that aspect of the image, what happens is when you pass that image, which now grid pixels, right? We're on the same page. When we pass that image into layer one, which is our input layer. So this is our image made up of a grid. We pass it into layer one. In ideal machine learning, it is passed as a list of numbers and not passed like this, right? So everything here is passed as a list, and that list is passed into layer one. Good. Layer one, in this case, would now scan the grid, scan it, and look for, pay attention to this part, it is looking for edges. The layer one, the input layer, scans the grid and is looking for edges. How do we identify an edge? Let's go back to the picture. Imagine I drew the picture of an emoji, right? This is an emoji, and I send this picture into the grid. How does it know that? How does it identify the edges in this picture? You will notice that, let's imagine now that this part, so I'm going to use numbers. So let's say that this part we have number 21. Then in this part we have number 86. Then this part we have number 87. But in this part we have number 22. What you'd eventually find out is that every single time that the numbers sharply change. Remember, we're going from 21 to 86, 86 to 87, 87 to 22. 21 to 86 is a sharp change, very high distance. In the system understands that this is an edge. Of course, there's going to be another number here. That number may be what? 2, right? But when there is such a sharp change between numbers, that is an edge. When there is another sharp change between numbers, that is an edge, right? The system understands that this place is a curved end. Sorry about that. Let me not soil our sheet. All right. It understands that this place is a curved edge, and it understands that this place is another curved edge because there has been a sharp change in the numbers. The numbers have changed in a very sharp way. That's an edge. So layer one is looking for all the edges in the image. That's the job of layer one. Now, what does layer one? After layer one finds the edges, what does it do? It passes it to layer two, passes to layer three, and by the time we get to layer three, another interesting thing will happen. At layer 3, the system begins to join the edges. But why are we joining it? Because remember we said that when we are passing the grid, we can't pass this grid into a computer. So we are going to pass it as what? A list of numbers. So if it was this list, it knows, it understands what each means. So let's say this is point location 0, location 1, location 2, and so when we're passing, he knows that okay, this was location 1, 0, 1, 2, right? He knows that. And now location 0 is probably the one that has 86, location 1 has 27, and then we pass that list. We are passing that list down to layer 1. Layer 1 knows all the locations, and he knows that okay, there was an edge here, there's an edge here, and then when he passes it down to layer 3 now begins to join the edge. It begins to join the edges. And remember that hidden layers, there are multiple layers, right? So layer 3 will join the edges in such a way that layer 3 would know that location 4 and location 9 is an edge. Location 26 and location 29 is another edge. It joins all the edges. It knows where all the edges is. It takes all the edges, and it knows that that edge is beginning to form a shape, because he knows that two curved edges close together might be an eye. it begins to pay attention to that, right? It knows that, okay, this edge, the way this edge is curved is an eye. The way this other edge is curved, it looks like a hole. Remember, it is only piecing it together. It does not have the full image yet because it is still collecting so much information from other layers. When it does that, it begins to pass what's that. So you can see the division of labor. Layer 1 has identified their edges here. Layer 3 is joining the edges and saying, oh, if you join this edge and this edge, oh, we have an eye. We join this edge and this edge, we have a nose. They will now pass that information to the next set of layers, and probably when you get to layer 7, right? So let's do this. And probably when you get to layer 7 begins to identify the joint object. So layer 3 is passing to layer 4, 5, 6, 7 that I found eye, I found nose, I found ear, but it does not know what these things are because it is still layer 3. It is identifying edges. It is joining edges together. When it goes to layer 7 will now say, okay, you found eye, you found nose, you found ear, oh, you found face. Layer 3 does the math. Layer 7 does the math. And it says, oh, ear, eye, nose, what do I know about these 3 things? I know that if there's an ear in a picture, if there's an eye in a picture, if there's a nose in a picture, and they are connected by this set of numbers, and they are so closely joined together, then that is a face. Now, layer 7 will now begin to pass face. Layer 7 is where you do, and I'm just saying layer 7, that's not how it works in real life, but let's just say layer 7. Layer 7 will now pass all the information it has down to all the layers. So maybe it will tell layer 8, layer 9, and layer 9 already knows that, oh, layer 7 found a face, layer 7 found a hand, layer 7 found a teeth, which is probably part of the face, right? And layer 7 found legs. This number 9 is the one that will be adding them together. Oh, let's add this, let's add this, let's add this. And when you get to say layer 15 will now recognize that, okay, probably at layer 12 will say this is a full human. Now, layer 15 will now say this human is Biodun. I don't know if that made sense. And here it's obviously not saying Biodun. It's probably telling us like, okay, I'm 90% confident that this is Biodun, or I'm 80% confident that this is Biodun. If you watched the last episode, you must have recognized that what we are talking about here is like the face unlock pattern. You pass the picture of your face to the phone. Your phone takes all the features of your face by layer, and it says, oh, okay, so imagine my face now, and it is passing it into my phone as a grid, and then it breaks down the matrix. So there's numbers, and then you arrange all the numbers in a straight line, right? Arrange it on a straight line. And then it passes that straight line into layer 1. Layer 1 identifies which part has eyes, which has part nose, which part has, layer 1 identifies the edges. Layer 1 identifies all the edges in the face, sends it down to other layers who are joining the edges until we get to layer 7 that tells us that this edge is an eye, this area has a nose, this area is an ear, oh, this is a face, and then it passes it down to continuous layers who continue to join the image until they get to layer Biodun, which is layer 15. Remember, everything is in numbers. Now, the machine in this case has not just seen pixels, it has understood context. The question the person might ask is, how does it know when to join, how to join this layer and this layer to be eye? How does it know how to join this layer and this layer to be ear? The machine is not doing magic. Pay attention to this. Remember we said that in systems, when we actually talk about training machines, we give it lots of training over time. So the machine knows that if I see, and now we're just using numbers, if I see 81 plus 87 plus 92, I am seeing ear. If I see 26 plus 37 plus 101, I am seeing teeth. Do you understand? So it is not randomly guessing, because if you come now and you tell it, oh, 21 plus 32 plus 101, it will most likely know that this is not teeth, right? It will know this is not the teeth. What we are saying is data. We have passed so many images to the machine in the training section. The machine has broken those images down into grids, which has broken down into pixels, passed it into the machine as a list of numbers. The machine has been able to identify edges and bring out the final results. We have trained it to know that when you see this, this is where you are going. When you see this, this is where you are going. And it has used that training over and over again so that when it sees a new image, it simply has to break it all down, pass it, look at the model, which is the data, right? All the things I've learned in the past. Now I'll look at them again and say, oh, based on what I know, whenever I see face, I see eye, I see nose, I see this is a human. And then it can even go further and we say, okay, if you see a black face, this is a dark person. If you see a white face, this is a white face person. You know the Caucasian because it is seeing pictures as RGB. And so whenever it sees a dark face person, it knows that a dark face person would have something around R, maybe the R of that person, the red of that person would probably be 21. The green of that person would be maybe 201. And then the blue of that person would be 186. This is just arbitrary guessing. And then when he sees something close to this, he knows that that person is a dark person. Okay, once again, I really hope we've been able to pass the points. But then, let's break it down simply put. Computer vision is everywhere, right? Remember we talked about your face unlock system. You see, whenever you pass your face into it, your phone is actually matching 30,000 dots, 30,000 infrared dots onto your face, which means it is mapping out those amount of pixels and it is matching patterns to be able to see whether that face you gave it initially when you were setting your security lock, whether that face looks like it. This is the reason why we're able to have systems that can detect cancer. Why? Because they are studying shapes of lumps. Bare minimum, right? This is what I'm saying. Bare minimum, when I say shape of lumps, there's so many other things they are considering, right? But edges. The machine already knows what cancerous cells look like. So when it sees cancerous cells, it's like, oh yeah, cancer. So if they tell it, oh, a perfectly rounded edge is not cancerous, but if it is not perfectly rounded, there is a likelihood of a cancer. The machine only studied so many examples and now can output results based on existing predictions. How do self-driving cars use this? Self-driving cars use this because they've been trained over time on what stop signs look like. They know that when they see something with an edge here and probably an exclamation mark, they already know from their training data that this means stop. They know red, green, blue, yellow for traffic signs. They know what humans look like, and that's why when the image captures a pedestrian crossing the streets, the car knows when to stop. They can do all of these things in real time. Look at the speed at which your phone unlocks with your face. Cars even use faster speeds because they cannot afford to delay in catching the resemblance between the data. Now, what we've come to understand so far is images are just numbers. And computer vision is science of teaching machines to find meaning in those numbers, layer by layer, pattern by pattern. Now, next episode, we're now going to talk about reading. Instead of how does a computer see images, how does the AI understand languages? How does it know that the little black boy passed the house on the hill? How does it know that that is a very big sentence? And how does it know that Bola is a girl is a very small sentence? This is where we get to the point of discussing NLP, natural language processing. And this is why you can chat with AI, you can send messages on Google, you can translate, you can use voice assistants, hello Google, hi Google, hello Siri, hey Siri, hi Alexa. This is where everything comes together. This is the core of natural language processing in artificial intelligence. So I hope this was very clear. You can watch the video again just to be able to get the understanding of it. But you understand now that even if you did not get anything, you should get that AI takes images as pictures. Images are taken as numbers. Numbers are put in a grid and are assigned pixels. Each pixel has a number. Especially for black and white images, they have a number. The image number tells us how bright or how dark an image is. And if it's a color image, it has an RGB format where it tells us how much red is in that image, how much green is in that image, how much blue is in that image, and combine it no matter how many times. It can give you any color in the world. So this is how your system knows color. All right, and then all of those things are now passed into layers of deep learning systems. One layer connects the edges, another layer connects the big bold forms, another layer connects the completed edges to form maybe eye, maybe nose, maybe teeth. An extended layer will connect everything to form probably a face, and at the end of the day, you're able to get human. Quite extensive, I do know. But however, for you to get the understanding of the full gist, it's very necessary that we go this deep. So once again, I'm grateful that you still joined us down to this point, and next week I'm going to see you on episode 12 of AI for Humans, where we discuss natural language processing. Bye.